Okay, so STM. How would I go about describing what STM is? First of all, STM stands for Software Transactional Memory, which per se doesn't really convey what it is about. I feel like the easiest way to grasp the underlying idea is by sort of making a parallelism with database transactions. What the basic concept of database transactions is that you have multiple changes and you want all or nothing to be committed. So, like in an SQL database, you say begin, then you do 2 or 3 row updates, then you might run a condition, and based on the check in the condition, you decide to either commit or roll back. For example, if we have any error that we didn't expect, we roll back, and all the changes do not appear for consumers of the same database. The concept is very similar to what STM is within the boundaries of a single running program, process, or whatever. The concept of STM comes from functional languages such as Haskell and similar, but really you don't quite need to know any of the history to understand what STM is about. And maybe let's just show briefly the underlying implementation, because it's actually quite easy in TypeScript, because we don't, like in other languages where you have true parallelism, the implementation is a bit more complex. Well, in TypeScript, thanks to the designers, we have a single thread, and that makes life substantially easier. So I'm here in the code base of 4.0 small, and in 3.0 we had a module which was called STM. Now STM is no longer a separated module, but I've implemented it in effect itself. So when inside effect you have a function called transaction, and you can see that from the type signature of effect.transaction, we are basically running an effect and removing from the environment a service which is called effect.transaction. Now there's a different function which is called transaction with, that gives you access to a state parameter. Let's see if yes, Mattia, the autocompletion works. That's good. Well, the idea now is that we want to see what's inside this state. Inside this state, you see that there's two things. There's a retry flag, and there's a journal. What is the journal? The journal is implemented as a map from this thing called transactional reference to a value which is a version and the underlying value. So basically, inside, let's say that let's import transactional ref to begin with. Let's say that here I say ref equal yield dxref.make 0. This is a value of type transactional reference. The journal can be used to get the value of a ref. This will give you the value, and it will give you the version if it exists. So if it is journaled. This to say that basically the whole logic around transactional references, which is the underlying implementation of STM, is the idea of providing a journal that keep tracks of changes before a transaction is actually committed. And when the transaction is actually committed, we end up taking the updated values from the journal and writing them to the actual references. So you can think of it like we have a journal, all the state is isolated in transactional references that are like atoms of values, atoms of data. And in one shot, we commit the full transaction. So anything we do within the body of the transaction is not observable from the outside. This is one key element. The second key element of STM is that it implements optimistic transactions. What are optimistic transactions? It means it tries to run the full thing, it tries to commit. If it fails for any reason, it keeps retrying. Now, the retry logic is much smarter than just a while loop. Basically, the retry logic means checking for all of the values that have been read during the transaction. And once any of the value changes, then we retry, which means we're not like wasting CPU on keeping retrying the same transaction all over again. We only retry when any state that we've read during the transaction have changed. Because
Mike, there
one
was
of the
a
principle, yeah,
quick request from the community if you could zoom in on your editor.
Yeah, I can try, but then nobody reads anything. Maybe this is
if you can do one more
better.
tick and collapse the files view a little bit more, I think that'll help folks.
I'm also trying to remove. I'm not sure if we're gonna use open code for now or not. I've removed it for now. Let's take a little bit more now. Now it should be good.
Thank you, Mike.
You're welcome. So basically, we're describing sort of the retry logic of STM and how we only retry asynchronously if stuff changes, because it's implied that transactions are deterministic, and it's implied that they're only dependent on state, on transactional state that we read during the transaction, which means if nothing in the state changes, then the result of the transaction would be the same. And there's no point retrying if nothing has changed. I can show briefly the implementation because it's actually quite easy, or at least it felt easier than what we have in V3. And you can see that inside the transaction with function, which is the boundary of when we run a transaction, the first thing we do is we create a new state, a new journal, basically. And okay, we take the fiber scheduler, which is probably a lower level thing, which is not so interesting. We run within a non-interruptible thing. Okay, this code was heavily changed by Tim. I can recognize the style.
Recognize the signs of Tim.
I recognize the signs of Tim. It was much easier when I implemented it. Now it's probably much more performant, but a bit less obvious. So we retry. So we run a while loop until we have a result. In the body, we restore interruptibility around the function. This is kind of very low level, doesn't really matter, but you see that we provide the state as a normal service. Recall that we created the state here. The map is mutable, the retry field is mutable, the state is very low level. You probably never have to interact with the state as a user. This is kind of a low level constructor. Then we say we tap the cause, and if we should not retry, then we simply return void. If we should retry, then we await for pending transactions. Okay, no, this gets way too complicated. Unfortunately, that's not.
Maybe it'd also
It
be
used to
good.
be easier.
Tim, uh,
Tim.
maybe it would also be worthwhile to motivate STM a little bit too, like because I'm sure the audience like is very interested in like understanding STM, but I think even for me sometimes the like utility of STM in a runtime like JavaScript, like you start to think about like, okay, well, why do we even need something like software transactional memory in JavaScript? So maybe motivating
I
STM could be
wanted to
interesting.
get there because my hope is that the implementation was obvious enough that it would then generate ideas
Yeah.
around use cases. Because
Not anymore.
I think the like if one thinks about STM as a way to handle transactions, it's not very interesting. When it becomes interesting, it's as a way of checking, basically as a synchronization primitive, put it this way, because of the logic around retrying as in an asynchronous fashion. And I can show that. One idea would be, let's do something. Let's create a semaphore. What is a semaphore? Well, a semaphore, we have it in effect itself. We already have one function called effect.make. Actually, we have a semaphore module. And the semaphore.make, we specify a number of permits, like we have one permit, and then we have a function which is called with permit, where we can run an effect. So like effect dot delay 1000 effect dot log hello port const run. So now I have an effect that is delayed by 1 second, and it prints hello world. Let's say I want to run this effect, repeat times 5, const repeated. Why are the types like this? Do I have to do it this way? I have to do it this way. Yeah, inference. Actually, let me also rewrite this in a slightly nicer way. We said effect dot delay 1000 effect dot no semaphore with permit. This repeats it 5 times, but actually this is not what I want to do, because I want to run this stuff in parallel. So maybe should I use the
We still have an effect.replicate.
sure replicate? Yes, we do have effect.replicate, which gives me an array. So times 5. Okay. Let's say effect.all concurrency unbounded. So if I remove the semaphore, if I remove the semaphore and yield this, what I see, hopefully, fact dot, actually we are in node.
And also, as Mike's writing code, if anybody has concrete questions about STM as he's like explaining things, please feel free to write it in the chat, either in YouTube or Twitch, and I'll make sure to relay the questions. Also, a cool thing is that I think that we
We no longer have TSX.
You can run with Node directly now because we're ESM
Yeah.
only.
No, I cannot.
What Node version are you on? 22?
Oh yeah, 22 is too old. Yeah, needs to be at least 24. Yeah.
Yeah, you can just do a -- experimental,
I think
or you can just install.
Nix.
You can just install TSX as well if you want to just get this running quickly.
Or I can probably do bun. This also means that we have a broken flake.
I'll have to take a look at it.
So you see, without a permit, I'm running 5 instances of the same thing. It prints 5 times hello world, all at the same time, because I'm waiting a second and then printing everything. Let's reintroduce the semaphore. And what happens now is only 1 per time is allowed execution. If I allow 2 permits, 2 at the same time are running. So a semaphore is a way of controlling concurrency of our program. And it's a really nice structure, but it has one issue. Let's say that I have semaphore 1 and semaphore 2, and I want to take both a permit on semaphore 1 and a permit on semaphore 2. Now, in this case, we would not have any issue because there are really no race conditions. But what happens here is that first I'm gonna take a semaphore out of semaphore 2, and only once I've taken a lock on semaphore 2, I'm taking a lock on semaphore 1. Which means if I have any conflicting transactions and one requires, for example, run 2, but it does it in a different order, if I run those 2 concurrently, they would deadlock. Because the first will take semaphore 2 and wait for semaphore 1. The second will take semaphore 1 and wait for semaphore 2.
It also may
And
be
neither
easier to
can
grok
complete.
this if you adjust the number of permits to a single permit.
Yes, probably.
Yeah, now it should be a little bit easier to grok.
I would still have to run like probably run 1, run 2, run 1, run 2, run 1, run 2. I'm not sure if we will deadlock. Hopefully we do. We do not. We do not, because why are we not deadlocking? Why are we not deadlocking? The funny thing is I've done the same example in the past, and I remember not deadlocking and then spending like 10 minutes understanding why I was not deadlocking.
You should like pull up the VOD and like remember what we did, because I remember that as well. I remember I was like trying to simulate a deadlock, and then
Let's see if the clunker is smarter than me.
well,
We
it's
are working
I can confirm it's smarter than me.
on.
So
Okay, I think we got a decent example. The issue here is that we are fundamentally we have a body. The final body is dependent on taking two semaphores, taking a lock on two semaphores. And if we do it on reverse order with unfortunate timing, we end up in a situation where the first process to continue waits on a lock which is taken by the second process, and the second process to finish requires a lock that is taken by the first. So we have the classical situation of we can't do anything about it, and it's dead. The issue is that taking a lock is non-transactional, which means we're taking the first, only then we're taking the second. This issue would not be reproducible if we took the two locks within a transaction. So take the first, take the second. If I fail to take the second, it's like nothing happened. I don't block the first. This is very hard to do unless you have something behind the scenes like STM. How do you build a semaphore around STM? Well, it's very easy. You fundamentally say we have a module which is called a transactional semaphore. I'm not going to use it because it kind of defeats the purpose of showing what a semaphore is. Let's actually say make lock. So a lock is a semaphore with a single permit. It's easier. Effect.gen const permits. We create a transactional ref with a simple number. Let's do it in the same way. We're creating a reference that keeps track of the number of permits. Then we have a constant take permit. And here we say const current permits, actually available permits, yield txref.get. Let's rename this to permits ref so it's clearer. Now we have a number of available permits, and we say if available permits are greater or equal than the number of permits we want to take, that's good. We can take the permit, which means txref.set available permits minus n on permits ref, and we return. Otherwise, we return effect.retry transaction. If you see at the signature here of this function, we now take a number, and in the result, we have effect.transaction, because we are reading references, we're doing checks, and we are retrying in case the transaction fails. Here I can also return the number of permits taken to make it easier. Similarly, I can implement a release permits. In this case, there's not much I should do except saying a plus. There's no case in which this can fail, so I don't need to retry in any case here. So now I have two functions that allows me to take a permit and to release a permit, and return. I can just return take permits, release permits. So what happens in this take permit function is, again, we check if we have a number of permits available. If we have enough available, we take them. If not, we keep retrying. This will retry only when the value of permits ref changes, which means we are fundamentally waiting for permits to change, and anytime there's a change, we check again. Are those enough? Yes or no? If no, we keep retrying. If yes, we take them and return positively.
So is this how you prevent like a busy retry loop with STM, sort of?
Yes, because the alternative would be a while loop, and a while loop would block the thread, so it would not allow anything to continue. So we would have to retry, for example, on next tick or similar, set a timer and retry every number of milliseconds. Instead, we have a very efficient auto retrying mechanism. The difference between this semaphore and the other semaphore is that now we can take two semaphores at the same time, because if we refactor this to our make semaphore, it will not succeed. But what I can do here is effect.all. Actually, now I have to say effect.commit, effect.transaction, sorry, effect.all, first.take, second.take. And this occurs in a single block. Same on release. I can do effect.transaction, effect.all, second dot first dot release.
You may have to change the types.
Yeah, I do have to change the types.
Or you could just change the return value of the, yeah.
The example was indeed fairly easy. I just needed to tell GPT that it should be 10 lines, or otherwise I will fire the model. And it did it in 10 lines. So the trick with the bad example is that I have basically a computation that takes two logs, AB, and then I have it BA, so that does it exactly in the opposite order, and I run them in parallel, which sounded very much like what I was trying to show at the very beginning, and it didn't deadlock. The thing is, when time is involved, it's hard to make things conflict, which is usually why you don't see the bugs locally when you have a one user that is hitting your API endpoint, which is yourself, but still things starts to fail badly once you deploy and you have more users doing the same stuff, because concurrency bugs end up materializing much more frequently, and race conditions starts to appear. So now I have this bad example which will never complete, because for BA to complete, AB has to finish, and for AB to finish, BA has to complete. Then I have a good example which does exactly the same thing, but it does it with transactional semaphores and acquires AB and BA transactionally. So if B fails to acquire, it's going to retry and not lock A. And we can see from running it that running the good example completes, and instead running the bad example ends up firing a timeout. That's a contrived example about STM, but the key unlock is this idea of being able to retry transactions up until your conditions are met. And you can do much more interesting stuff, which is like we have various transactional modules. They all start with TX. There's a TX chunk, there's a TX deferred, there's a TX hash map, hash set, there's a priority queue, there's a pub sub, there's a queue, there's a reentrant lock, subscription ref, and we'll add more in the future. But with this, you can do stuff like push to a queue and publish a message to a pub sub, or pull objects from a queue only if there are more than 5, wait for conditions on the number of elements inside a queue before you do something else. You can architect these more complex condition dependent processes that would otherwise be very complex to organize. And
I think
I've
that was the
shown
I think that was the exact example we used, if I remember, like going back to the stream we did a while back, it was the queue example. We switched from like the semaphore business and we just decided to use the queue example because it was a lot easier to like reason about.
I think the example that I was trying to architect last time was the idea of taking from multiple queues. Let's say you have like 5 queues and you have one job that should take an element from either of those 5 queues. Doing that with normal queues would be very complex, because you have no way of waiting for the condition when there is an element in the queue without taking it. And once you took it, you took it. Let's say, for example, you have a queue of tier 1 requests and a queue of tier 2 requests, and you should give priority to one queue versus the other. It's extremely complex to achieve those without transactional queues. With transactional queues, instead, it's very easy, because you can have a condition check, and you can have the takes as part of the same transaction, which means if the conditions are not met, you're not changing anything. If the conditions are met, you take the elements without breaking any other worker which is taking from the same queues. Like, doing this kind of synchronizations is weirdly complex, and you can see the difference between, like, I've shown the how to make a semaphore locally before, but if we see the transactional semaphore that we have in the library, it's quite literally the same thing. It creates a permits ref, and then it makes the semaphore, which is just an object with a permits and capacity. and taking a permit. So acquire takes one permit, is exactly the same code that I wrote before. It's like if I don't have an available permit, I keep retrying. So I've shown exactly the same code that we have in the library, while instead I can show the implementation of a semaphore. And you can see the stuff like taking. This is much more complex, even for a simple thing like a semaphore, because we have to keep track of waiters, so people that wants to take a permit when the permit is not yet available. We have to synchronize things properly. Like, this code is much more complex compared to just basically this. Like, this is what you would like to write versus the other. The reason we also have a non-transactional semaphore is because transactionality adds a cost. So obviously creating the journal, the whole infrastructure around retrying on the journal, and so on and so forth, is non-trivial, and it adds a little bit of cost. And for very high performance hotspots, like, we use semaphores in weird places inside core, it would be not ideal to pay that cost all the time when we have a low level alternative. But if we erase perf as an argument, there is no point in the library having structures like a queue, like a normal reference. We could make everything transactional, and it would be easier to express some of the concurrency problems that we have internally. So from a user perspective, it's not too often the case where you need a transactional implementation, but many times when you end up, like, for example, a friend of ours, Johannes, has a lot of concurrent stuff in his own UI work, and it's very frequent that he has to do stuff like taking an element from different queues and stuff like that. And for this, STM is perfect. I apologize that the example was not ready to go, but the reality is generating deadlocks and race conditions is hard, and these kinds of prove it. It takes a while to get to code that doesn't work reliably.
No, I mean, I think this was great, and it's also more fun to try. In my opinion, watch the process instead of coming with like a full example. And in this case, the process just being you fighting with Jippity.
I thought you were about to say it's so fun to see you fail at, at
That
writing a
too,
piece of code.
I try to be nice and not say those things, but in my mind,
Yeah, I've
that's what
heard it
was
from your mind.
that is what's going through my mind. Just trying to reset, because everybody in chat's trying to inflate the ego, and I'm just trying to like bring it back.
Deflate. Okay,
Um,
makes sense. Makes sense.
It was
let's see.
interesting to see you try to get to the actual situation, to the actual error that the module tries to solve. Yeah.
And well, I get the idea is much broader. It's about transactions in general, but I find it that often we get a question of the type, why is STM necessary in JavaScript that's single threaded? And the question makes sense because in other languages, STM is used primarily to avoid race conditions and build concurrent data structures that are lock free, and they use optimistic retries. And initially, I was under the same impression, which is why in the first version of Effect, I did not port STM over. But later, I realized that big part of STM was waiting on asynchronous conditions, and this makes sense in JavaScript because in JavaScript we have async. We can have concurrent processes. We don't have parallel processes, but we still have concurrent processes. So for many scenarios like the ones we described, STM is the way to go.